If you want to go to Mars, you should start losing some weight. Welcome to The Big Puzzle. In this podcast, we explore the subtle connections between science, religion, politics, economics, and history. One piece at a time, we unveil the big picture of this shared experience that we call life. The last piece of the puzzle about this topic, having a city of 1 million people in Mars, we talk about the 4 fundamental forces in nature. And we address the problem of nitrogen and connect it to the strongest of those forces. That's a strong interaction. How it's possible but very, very difficult to do nuclear transmutation. That means to transform one element into another. But today we're going to be talking about the weakest of those 4 fundamental forces, and that is gravity. And even though it's the weakest, is still posing a big challenge to space exploration in general, and establishing a city in Mars in particular. When we think about gravity, we might think about astronauts floating in space, the ISS, the International Space Station, and all these people floating around and sending videos and conducting experiments. And we might think, well, that's what happened when you go to space. Actually, there's no gravity in space. But that is not true. Actually, at the elevation, at the altitude at which the ISS is flying, there's almost 90% of the force of gravity compared to the surface of the planet. And I know technically we're talking about the acceleration of gravity, but to keep this casual, let's just talk about the force of gravity. And so if it's 90% of the gravity is still there, 400 kilometers over the surface of the planet, why are they floating? How is that happening? Well, actually they're not floating. And if you're a flat earther, hold your horses, because you're wrong. Gravity does exist. But what's happening in the ISS is that the astronauts are not floating, they are falling into the Earth. The thing is that the whole station is falling as well. So it's like, if you would be in an elevator and then, it breaks and start falling and you're inside of the elevator, well, you will feel like you're floating inside of the elevator until you hit the ground, and then you realize that you're not floating, you were falling. But how is it possible? How could the ISS be falling for this long and haven't crashed yet? And that's an interesting thing. It is falling, but it's always missing the planet. How does that work? Well, if we think of the Earth as a sphere, well, it's not technically a sphere, it's a spheroid or an ellipsoid, or more likely a geoid. That means that it has the shape of the Earth, but it's approximately a sphere for our purposes. So what you need to do is to have a tangential velocity that every time that you're about to fall into the Earth, you keep missing. So you end up circulating around that sphere, and always falling into it, but your horizontal velocity is so fast that you're always missing it. And that's what we call an orbit, right? So they're in an orbital velocity. That means that the International Space Station, it's falling, the astronauts are falling, but they're always missing the Earth. And that could happen pretty much forever. The reason why it wouldn't last forever is there's something that would decrease that velocity. At 400 kilometers, the atmosphere is so thin that the friction is really small, but it's not negligible. So once in a while, the International Space Station needs a boost because it starts losing elevation, and they lose elevation, also the friction increases. So it needs to get some boost to regain speed and also regain altitude. So if you can find in the web places where they show the change in elevation and when they're producing these boosts. Interesting, when they produce this boost, the astronauts and everything in the station has to be strapped because suddenly there's a lot of acceleration. And yeah, those people that are floating, suddenly they're thrown back, or quite the contrary, the space station is thrown ahead, and they could hit. So that's a very interesting thing that happened with the International Space Station. But that doesn't mean that there's no gravity there. Still, as I mentioned, it's about 90% of the gravity that they will have in the surface of the planet. But what about much farther away from the Earth? Does gravity still apply there? Does the gravity of the Earth still affect you if you're very, very far? Well, yes, it does, all the way to infinity. The thing is that the force of gravity decreases fairly fast. The way it decreases is by the inverse of the square of the distance. That means that if you're twice the distance, you have 1/4 of the amount of gravity, right? So yeah, theoretically, even if you are in the limits of the universe, you will still have a tiny, minuscule, indetectable attraction from the Earth. So what if we want to really go into space, not just be falling in an orbit around? What if we really want to go, for instance, to Mars? How do we escape gravity, the gravity from the Earth, to a point that again, it doesn't have much influence? That is what is called the escape velocity. How do we determine what the escape velocity is? Well, let me explain it to you with one example. Let's start by simplifying the problem as much as possible. So let's ignore the atmosphere. There's no friction. Let's say that the Earth, is just a perfect sphere of uniform composition. And let's say there's nothing else in the universe but the Earth, right? So if you throw an object into the air, you will be given some initial velocity, but that velocity will slow down because of the force of gravity, the acceleration of gravity, and eventually will just come back down, right? So you could throw it faster. And yeah, it will go higher, but eventually it will stop and it will fall down into Earth. Now, if you could give that object sufficient velocity, sufficient speed when you send it up, it will slow down, but it will reach zero velocity at the infinite distance, right? So that is what we call the escape velocity. That velocity that when you throw something, up, it will be slowing down, but when it reaches zero is when it reaches infinity. So it's a calculation. Obviously, there's no infinity, but you can do with all those simplifications, those calculations. And for different planets with different gravity, surface gravity, the value, the escape velocity is different. For the Earth in particular, with about 9.8 meters per square second of acceleration, you get that the escape velocity is 11.2 kilometers per second. So now if you don't use the metric system, and especially if you're American, that's the equivalent of 100 football fields per second. So if you send something up at that velocity, again, ignoring the friction with the atmosphere and everything else, then that object will never come back, will never fall down, because when it stops, it's actually at infinite distance. So, well, it's not that hard. You just need to accelerate stuff, right? So let's use one simple example. Let's say that we want to send you out of the Earth. And let's say that you weigh 200 pounds. I wish I would weigh that, but yeah, that's kind of the average weight, at least for men in America. So yeah, you weigh 200 pounds and we want to send you, to infinity, so you won't return to the Earth. We can calculate how much energy you would need to do that. And to make numbers that we can understand, let's say that we're using gas. So your car's fuel, how much energy, how much fuel, how much gas you would need to send you to infinity, to the escape velocity. And the calculate, if well, obviously the fuel has to be, the efficiency has to be 100%. So you have to extract absolutely everything from the fuel. If you think about internal combustion engines, well, the efficiency is about 25%. So you can see that we're being, very generous. But if you could extract all the energy from fuel, how much fuel would you need to go into space and never come back? Well, the number is about 1.33 times your weight. So like I say, if you're 200 pounds, you will need 266 pounds of fuel to accelerate you to that velocity, to that escape velocity, so you can, leave the Earth for good. It doesn't look that much, right? So it's something that you can visualize, and yeah, it's pretty much the same size of fuel, just 33% more. But there's a problem. To explain what the problem is, let me tell you a little trivia that you maybe never thought about it. So if you drive a car and if you drive alone, 94% of the fuel is used to move the car and to move the fuel. Only 6% of the fuel is used to move you. So that's why cars are so inefficient, because most of the energy is used to move the engine, to move the whole car, and you're just a small part of it. Well, this also applies to your problem about leaving the planet. So if you want to leave the planet, well, first of all, those 200 pounds is you just naked. And you wouldn't survive for long in space being naked. So you need to have some kind of capsule, some kind of, spaceship. And that spaceship has to be able to support an internal pressure close to, 1 atmosphere, or as close as you can to 1 atmosphere. So you would feel, like you are in the Earth. And 0 atmosphere outside, right? So vacuum outside. So it has to have some structure. It has to be, sturdy. And also it's something that will be accelerated. So it has to deal with those forces as well. So those 200 pounds suddenly become much, much more. If you're going to be traveling for months, well, you need to take all the water, you need to take all the food, you need to take a ton of other stuff. So that makes it, a lot more complicated. But that's not the worst thing. The worst thing is that you cannot apply all the energy while you are in the Earth. You can go from 0 to 11.2 kilometers per second in a fraction of a second, kind of in an explosion of all that gas. Because, yeah, you would be squeezed by the acceleration. So you have to reach that velocity by an acceleration that your body can survive, right? And 2 or 3 Gs probably are too much. It depends for how long. And so that means that the energy has to be applied through time. And that's where the problem lays, because you need to take the fuel with you. Now, if you're taking the fuel with you, that means that you have to add that weight to the things that you need to carry with you. So that means that you need more fuel just to take you and the fuel. And that means that you need to take more fuel to take you and the fuel and the fuel, and so on. Right? So that in the Earth makes it very, very difficult to leave the planet. That's why rockets are so big. Most of the rockets are just fuel. And then, the payload is relatively small, less than 10% of the total weight. So really the problem is that you need to take with you all the energy to eventually accelerate. But if you're going to go to another planet, well, then you need to lose all that energy. You're traveling at 11.2 meters per second, and you need to go to zero to stop. And in the Earth, well, usually you would do that using the friction with the atmosphere to lose a lot, to drain a lot of that energy into heat, right? And so your velocity slows down, but you still would need something at the end. If you've seen some of the rockets now that are coming back, well, you need a final burnout to stop, basically. Or some other cases, you need parachutes or some other things to actually stop you to zero when you reach land or the sea. But, well, if you go to Mars, the atmosphere is really thin, so it won't help you that much to stop. That means that you need to take also enough fuel to stop, right? To lose all that energy that you gain when you were leaving the Earth. Now, think that you also want to come back. Well, you need a lot of fuel now also to be able to depart Mars. And even though the atmosphere and therefore the escape velocity, the atmosphere and the gravity, it will require much less energy to leave Mars than to leave the Earth. But taking all that, even if it's small, is very, very difficult. And some people would say, well, but we can't generate fuel in Mars. Yeah, we talk about that. They say they can create methane from the carbon dioxide and water, because you need hydrogen. Well, you need to find water, you need to have enough energy to extract, to create it. We talk about that in one of the other pieces of the puzzle. So yeah, it's not happening. So creating the fuel to come back in Mars, it's very, very difficult. It requires a lot of energy to do that, and a lot of infrastructure that you have to take there with all the problems that we already have. So interesting that there's an equation that determines how much fuel you would need, or the proportion between fuel and payload. That's the Tsiolkovsky rocket equation. You can look it up. You can find the derivation if you like those things. That explains the thing that I was saying. So how taking the fuel with you, makes you use more fuel. As a side note, I'm still on the fence about having stages of the rockets coming back, because, like I said, yeah, they're reusable. It has to be seen if it's cost effective. I really don't trust the numbers that are shown. The stresses and the heat and everything that these rockets have to endure, yeah, they're not like planes, right? So the materials suffer a lot. I don't know if I would trust my life on a rocket that has been used 10 times, right? There's way too many things that could fail. So having rockets being reusable, they make them less efficient, because now you have to take fuel that you're not using to gain speed, but to decrease energy. That's why the space shuttle, it actually used exclusively the friction, and then it would glide down. that's the way it lost the energy. So finally, the last energy was lost by breaking when it landed. I think that made way more sense than what SpaceX is doing now. It's really cool, yeah, but I don't think it's personally. I don't think there's much to gain with that. I don't think that rocket, with the technology that we have now, would be reusable as planes, like the claim that they make. I mean, no. As an engineer, I wouldn't trust on that. So that is one of the main problems. Not only the conditions in Mars, like we talked before, but how to get there, and all that involves. Now, for the last, I don't know if it will be the last, but the most important piece of the puzzle will be related to this in particular, because we talk a lot about energy, but at some point, energy is money, right? And all the things that could be done with energy, that means that they require a lot of money. So in the next piece of the puzzle about this, we're going to be discussing the economics of space travel, the economics of Mars and its potential city in Mars, and the future, and so on. The homework then for that is a preparation for this next piece of the puzzle. It will be very expensive to take things to Mars, right? So think about all the things that surround you, all the things that are in your room, in your house, your city, and try to estimate what is the weight of everything. That's something that we usually don't do, but I think it's a good exercise, because all those things that you would need in Mars have to be accelerated to escape velocity and then decelerated. So that will mean a lot of energy and a lot of money. So I would challenge you to do that, to just look around and say, okay, if I would go to Mars, what would I take? What would I like to have there? My computer, would I like to have, my car, whatever you say you think that you would like to have if you go to Mars. And think about the weight. We will be talking a lot about that, about the weight and some other considerations. So do that, and the other homework is the ongoing one of being nice to this planet, because we're stuck with it for the foreseeable future, unless there's a new, very big revolutionary change in science, in physics, that we discover how to create wormholes or something as weird as that. Well, then, yeah, we're not going anywhere. And even if we could go to Mars, and even if we could create a tiny city there, that won't solve the problems at all that they're claiming they're trying to solve. So how can we be nicer to this planet? How can we be nicer to, the other living beings, and especially how can we be nice with each other? So with that, as always, I want to invite you to like this video if you liked it. Even if you didn't like it, you can still like it. Nobody's going to be, stopping you for doing that. You can subscribe if you like this kind of discussions, and you can share it with other people, some crazy friends that like to think about these kind of problems. And well, with that, I hope to see you the next time that we place a piece of the big puzzle.